Okay, welcome everybody. Good afternoon. Welcome to our monthly QuantEP seminar series devoted to the interface of quantum information theory and high energy physics. So today it's an honor and a pleasure to introduce to you the speaker, which is Saverio Pascazio from University of Bari, a colleague and a friend that has worked for since many years on different aspects, starting from foundation of quantum mechanics, quantum information theory, some very famous works on the Zeno effects, and since some years he has been involved in exploring the interface between high energy physics and quantum information theory. So please, Saverio, the floor is yours, and we are eager to listen what you are going to tell us today. Let me only, remind to everybody that we are taking questions at the end of this seminar. People attending at Zoom can raise hand, and people listening from YouTube, please write your question in the chat, and then we will take them at the end of the seminar. Saverio, please.
So thank you very much, Simone, and I would like to thank all of you for being present, virtually present, and for the invitation, of course, to give this talk today. So let me share the screen and start the seminar. Can you see my screen?
Yes.
Okay, I go to presentation mode, and I hope you can still see the...
Yes,
we can.
Okay. So today I will be talking about dimensional reduction of gauge theories and quantum simulations. And let me start by saying that this work has been done in collaboration with a number of people who are listed below. These are the names in red: Giuliano Angelone, Rocco Maggi, Elisa Ercolessi, Paolo Facchi, Davide Lonigro, Beppe Marmo, and Francesco Pepe. They're all Italians, so this is in a sense, a local seminar. And many of these people are involved in the quantum HEP activity, so it is a pleasure also to introduce the activity to all of you. So let me start by asking a question. So why should one think about worlds, about possible worlds with n space and one time dimensions? Which kind of question is this? And before I even ask this question, I would like to ask another question. Why are we interested at all in a topic like this, about n+1 dimensional theories? Well, first of all, the main issue, the main reason is the paper by Feynman in 1982, the idea by Feynman that one should simulate physics through by using quantum mechanical means. So this is maybe the main motivation. The second motivation stems from early work by Wilson and then Kogut and Susskind, and I quote two seminal papers, but there have been a lot of people thinking about this, about lattice gauge theories. So when you try and discretize space, and this is called a lattice gauge theory. So you discretize space, and on the lattice, on the points of the lattice, you place a field, which can be a bosonic field or a fermionic field with some differences that are interesting to analyze in themselves. Now, these simulations, they lead to the issue of confinement of quarks, so therefore to QCD. And also, when you tackle these problems through quantum simulations, you overcome a lot of difficulties. I will try and briefly tell you which difficulties you overcome. And let me emphasize that you overcome lots of difficulties, but not all of them, for sure. So there are some difficulties that still remain when you try and use quantum methods to analyze lattice gauge theories. When you look at lattice gauge theories, there are a lot of very profound questions and also very interesting novelties. For instance, you discretize space-time, you look at bosonic versus fermionic fields. These are very different fields, and they should be dealt with differently. You have new phenomena that come in. For example, fermion doubling, just to mention one thing, which is very interesting in itself because it makes you understand better the structure of space-time. And among the interesting novelties we have when we look at this, when we tackle these issues with quantum simulation, there is for sure real-time dynamics, in my opinion, and then also the efficient calculation of what I would call standard quantities, for instance, related to the S matrix. So you have a quantum, I don't want to call this a quantum advantage because we are not yet in that regime. However, I think it is interesting to understand that there are things that you can do by quantum methods that you would be unable to do with classical methods, even when you come to the computation of standard quantities. Okay, among the novel effects, I would mention just one effect, which is related to electrodynamics in one dimension. This is a typical novel effect when the dimension is not 3, the space dimension is not 3. Essentially, when you place two charges on a line, the electric field is confined between the two charges. So the energy scales like the square of the electric field times the volume, which is the length of the segment between the 2 points, the two charges. And therefore, this energy grows linearly with volume. It's immediate to understand that if you try and separate the two charges, you have to overcome a huge energy. There is a huge energetic cost, and you cannot do this. And this was taken as, the forerunner of what we would call nowadays a confinement mechanism. This mechanism, unfortunately, works only in one dimension for QED or QCD, or it does not work if you go to 2 dimensions and to 3 dimensions. So this mechanism is only valid in 1D. However, there have been a lot of founding fathers of quantum field theory, among them Schwinger, Coleman, Kogut, and Suski that I quoted, Kasher, Toft, Parisi. They all thought about confinement mechanisms within this framework. So this is one of the many issues that one can consider when one reduces dimension, and one hopes to get a glimpse at how these theories may look like and what they may tell us, if at all, they can tell us something new about the structure of space-time and the structure of field theory. Okay, so now, so far so good with the motivation. Now, there is a vast literature. The literature is very vast when you go to the quantum simulation of lattice gauge theories. And it is simply impossible to cite even the most important papers. So I decided to cite 5 papers. Why? Well, some of these papers are really seminal. The first one is, in my opinion, a very, very interesting paper. And so it must be quoted. The other paper, I quote the other papers because they are related to the activities that you are doing within in quantum HEP. I try to emphasize the role of INFN here, because in quantum HIP, there is INFN, it's one of the nodes, it's led by Simone. And you can see that some collaborations were already going on between BA stands for Bari, BO for Bologna, so between Bari and Bologna, between Bologna and Padova. And so this collaboration had been going on. Also, there have been some very fruitful exchange of young first students, then PhD students, then postdocs. And this, in my opinion, has led to an interesting feedback among all groups involved. So I cannot quote the whole, even a part of the literature, but I wanted to make you aware that the INFN component within quantum HP is giving a contribution. And there is Simone, for example, is certainly taking a leading role in these activities. So forgive me if I don't quote the relevant literature, but if you read the papers, you find at least, minimum, you have to quote 40 papers on the subject. Okay, now let me go to the topic of the seminar in itself. Now, I give you a bit of history. Does it make sense to think about worlds with n space and one time dimension? Is this an interesting is this an interesting topic? And does it make sense at all? Well, let me say that there is a very beautiful seminal paper by Ehrenfest in 1918, in which Ehrenfest argues that 3 dimensions, so n equal 3, I remind you that I talk about n plus 1. So when I say 3, I mean 3 plus 1. So n equal 3 is somewhat special. Why is it special according to Ehrenfest? Because the number of components of the electric field and the number of boosts equals the number of space coordinates, and this is n, this is 3, this is, sorry, n in general. On the other hand, the number of components of the magnetic field B, this is related to the number of possible rotations. So it's the number of 2-dimensional hyperplanes. And this number is n times n plus 1 divided by 2. So these two numbers, the number of components of the electric field and the number of components of the magnetic field, are not equal. They are equal only if n equal 3. And according to Ehrenfest, this is what makes n equal 3 special. It's the fact that the electric field and the magnetic field have the same number of components. If n is different from 3, E and B are somehow different. They have a different number of components. Now we are in 2020, 2022. I'm not sure that this argument stands as it would stand in 1918 after 100 years. Nonetheless, it is an interesting argument. So I would like to present this argument by Ehrenfest as a historical curiosity nowadays. So 3 dimensions are somewhat special. A little bit of history. Hadamard, in 1923, so 5 years later, independently, invented the so-called method of descent. Essentially, Hadamard observed that if we have equations with m variables, M for Mike, not N for Nick. If you can integrate this equation for n variable, then you can integrate this equation for n minus 1 variables. He was interested in the wave and the heat equations, so he was interested in a very specific problem. And the method, Hadamard's method, consists in noticing that he who can do more can do less. So if you are able to integrate equations in m variables, then you can integrate those equations in n minus 1 variables. In a few words, the method by Hadamard consists in assuming that the equations do not depend on one of the variables. So let me try and understand how this method works. So the question is the following one. How would the world look like in 2 or even 1 space dimension? So we talk not 3 plus 1. Let's think about 2 plus 1, 1 plus 1. And for the motivations I gave you before, let us see whether this is interesting for us from the point of view of quantum simulations or from the point of view of quantum field theory. Now the question, how would the world look like in 2 or even 1 dimension? This is a very difficult philosophical question or semi-philosophical question. It is clear that I am unable to answer a question like this. So I will be contented with a much simpler question. The question is the following: which form can the laws of electromagnetism take in n less than 3 space dimensions? So this is a much simpler question. Now I would like to emphasize that this is already the way I'm formulating the problem. It's because, first of all, I want to have a procedure. And second, there are much more complicated questions that one may ask. For example, how would the world look like in 3 space plus 2 time dimensions? Is this a possible world? What does it mean to have 2 times? Now, these questions are not academic. There have been attempts in the past to quantize theories in 3 plus 2. And these attempts have given insight and feedback. So already in formulating the problem in this way, I'm already reducing the question to a much, much, much simpler question. So I want to know which form can electromagnetics take for n less than 3, not QCD. electromagnetism, classical electromagnetism. Okay, let me be concrete, and I start being a little bit technical. Take the field tensors. F is the field tensor for electromagnetic, G is the dual, J mu are the sources, and I simply write the Maxwell equations. I'm sure you are all familiar with this. These are the Maxwell equations written in tensor form. And I've written them explicitly at the bottom, at the left, at the right bottom of the slide. Okay, let me emphasize that F mu nu, the electromagnetic tensor, is made as this very particular structure. The electric field is above, and it's a vector if the problem is time independent. The magnetic field instead is in that 3 by 3 sector of the matrix. So there is this very peculiar structure of the electromagnetic tensor. I will say that this structure is a tensorial structure. In other words, the theory can be derived by a tensor. And the Maxwell equation take that form. Okay, good. If I write the Maxwell equation explicitly, you get 8 coupled differential equations. These equations are simple. These are first order differential equations that involve the derivative with respect to 1 time and 3 space coordinates, x, y, and z. So ddt, ddx, ddy, and ddz. And 6 fields, the 3 components of the electric field and the 3 components of the magnetic field. And these are parts of a tensor. Okay. Now let's apply Hadamard's descent. Hadamard's descent means that you want, you request, you demand that these variables, your dynamical variables, the electric and the magnetic field, do not depend on z. In other words, you start putting those derivatives to 0. For example, dzbz, the first one, is 0. And then you go on through all the equations and you assume that these fields do not depend on z. Needless to say, I pick z, but if you pick x or y, it's the same. Not if you pick t, presumably. Okay, what happens if you apply Hadamard's descent? So if you assume that the fields do not depend on the z coordinate. Interestingly, this set of differential equations decouple in 2 sets. The 2 sets are the sets written on the right of the slide. Now, I will call the first sector, I will call it EEB. The other sector, I call it BBE. Why? Because the first sector involves 2 electric field components and 1 magnetic field component. The other sector involves, by contrast, the 2 remaining components of the magnetic field and the only remaining component of the electric field. So it is magical. This equation split into 2 sectors. Okay. Now, Rocco, who is one of our PhD students who is extremely talented in this, he did his master thesis on this. He managed to draw a diagram. So he managed to reduce this decomposition to a drawing. The diagram is what you see below. The Maxwell equations are on the picture on the left. And when you assume that the variables do not depend on z, these 2 sets of equations decouple. And you can figure out how this happens by looking at the diagram at the picture on the right. I think this picture is beautiful. So we published it because it's very nice, in my opinion. And it took Rocco. I would not be able to do it. Rocco is one of the co-authors I was mentioning at the beginning. Now, the 2 sectors refer to the red and blue components of the electromagnetic tensor. So, for example, the red component, let's talk about tensor F, not about tensor G. The red component is a tensorial structure, as you can see. It involves EX, EY, and BZ. The blue component of F mu nu, on the other hand, it's a kind of vector. It involves EZ, BY, and BX. Notice that the red component has sources which are rho, JX, and GY. These are the sources at the very right, the sources above in the J mu vector, 4 vector. On the other hand, the blue components of mu nu have only one source, Jz. Let me go back to the previous slide. That's the previous slide. Look at it. The EEB sector is 3 sources, rho, Jy, Jx, and Jy. The BBE sector is only one source, Jz. Only the EEB sector is a tensorial structure. That's what comes out of the calculation. So now you understand what I was aiming at when I said I want a procedure. Because, of course, we can look at theories in 2+1 dimensions. However, I want to ask, is there a mathematical procedure? A procedure is always arbitrary, but at least it's clean, because if you want to criticize me, you are free to do it, but then you have to go back and criticize the procedure I'm adopting. So I'm using a procedure, which is Hadamard. I assume that the fields do not depend on Z. And this procedure leads me here. So you don't like it? Fine. We go back to the procedure and we discuss the premises. Okay. So far, so good for the mathematics. But we are physicists, so we want to understand what does it mean? What is the meaning of this? Well, the EEB sector is a theory in which cylindrical currents and lines of charge interact like in the picture on the top left. When you integrate out the Z variable, you have the picture on the bottom left. You have an elementary current. You may call this a monopole within quotes. It's not a monopole. Let me call it a monopole. It's an elementary current interacting with the charge. A point charge, this is red, and the elementary current, which circulates in the XY plane. This is the EB sector. Physically, it means this. The BBE sector, on the other hand, are lines of current in 3D. When you integrate out the Z direction, this is become point something. You may call them charge, current. It's difficult to say because I would like to remind you that the source is Jz. And unfortunately, this is a Coulomb source. It will lose all characteristics of being, let me say, a current. This is the reason why we are drawing this source as a point. So the two sectors stand independently and they come out of Hadamard's procedure. By the way, the Lagrangian also splits in LEB and LBB. And if you are curious to know what LEB and LBBE look like, just look at the two equations below. Of course, it's complicated if you look at the tensors. Just look at the final result. You know what the Lagrangian of EEB looks like is E squared minus B squared plus the current coupling. Look at the final line, the central line, the final line of LEB. And the same is true for LBB. It's again E squared minus B squared plus a coupling in JZ-AZ. So the Lagrangians are familiar in a way. They all come out of Hadamard's procedure. There is a catch here. There is a caveat. The catch is when I derive the Lagrangian, I'm working with potentials. Let me go back. Here, I was working with fields. When we have fields, we don't discuss. Fields means forces. You push and pull. When you go to potentials, the story is different because there is gauge invariance. So I have, in some sense, to manage the gauge. However, if I manage the gauge correctly, the Lagrangians are decoupled, and they take this expression. You may question the way I manage the potentials. Unfortunately, I have no time to do this. So if you are interested, you have to read the paper or ask for specific questions. But beware, working with fields and working with potential are two very different things, also conceptually. Oh, symmetries, I don't want to talk about symmetry. They are interesting, but I have no time. Okay, so far so good. From 3+1, we went to 2+1. How did we do it? We applied Hadamard. we get two independent electromagnetisms with an S. And these two theories are possible and they stand. No other theory is possible, no other electromagnetism, if you apply Hadamard. If you don't apply Hadamard, probably something else is possible. But if you apply that the fields do not depend on Z, these are the only two possible theories. Okay, shall we go now to 1 plus 1? Let's remove we remove the Z dependence, let's remove the Y dependence. Okay, again, I have to assume that the fields do not depend on Y this time. So I have to take the two sectors and cancel the Y derivatives. What happens? Interestingly, we obtain 4 independent sectors. The 4 sectors are described by the equations on the left-hand side. I will call the first sector the E sector. Why? Because it involves only one component of the electric field. The second sector is EB, because it involves one component of B and one component of E. The other sector is the same as the one above. It's essentially the same by symmetry. And then there is a BX sector, which is trivial. The equations are 0. The first sector is the only tensor. This is the famous sector considered by the founders of the theory, by Schwinger, Coleman, Jakiv, Susskind, and so on. It's this sector. This is the sector that we study when we do our numerical simulations or quantum simulation. And there is also this beautiful experiment by the group in Innsbruck. And it's essentially, they are dealing with this sector by the group by Rainer Blatt. The two sectors, the other sectors are independent. And notice that in the second sector, there is wave propagation. So this is already a catch. In the first sector, there are no waves. In the second sector, there are waves. So this was an interesting discovery for myself. When you say that in QED, in 1 plus D, there is no wave propagation, I'm sorry, you have to define what you're talking about, because there is one sector that comes out of a procedure in which there is wave propagation. And this sector is the second sector. It's not a tensor, but it is a bona fide sector. It's a theory. It's one of the 4 possible theories. Rocco, who I mentioned before, managed to draw all this again. So the picture on the left, I'm sorry, these are the 2 sectors in 2 plus 1. And you can break these 2 sectors into 4 independent sectors. And this is what Rocco did on the very right. Look at the tensor structure. F mu nu decomposes into a lot of components. The only sector is, look at F mu nu, the only sector is the sector in red, the only tensor. The other sector are components of vectors. And the sector in blue, in light blue, right bottom, this is the trivial sector. It's trivial because there are no magnetic monopoles, of course. Also, the sources decompose, and they decompose accordingly, in such a way that the equations are independent. Let me glance again at the equations. You see the equation with the sources? They are interesting to look at. It's not, I don't say it's interesting because it's working. Most of the work was done by Rocco Maggi, so it's not. Let me emphasize that it is interesting because it's electromagnetic, so we are all familiar with the theory. Now things will become more complicated. That's why I'm apologizing in advance. Okay, what's the meaning? The meaning of this is, again, these are you are integrating out X and Y. So an elementary charge is nothing but a plane of charge, half of a condenser. In 1D, this plane of charge, this is the picture at the bottom left, this becomes an elementary charge. This is the charge that is quantized by the founders, by Schwinger, Coleman, Jakiv, Susskind, and so on. This elementary charge is this one that you see on the bottom left. It's a plane. By the way, the other charge, this is a plane of current. flowing towards the y direction, and it is an independent electromagnetism that admits a quantization in principle. It's not a tensorial. It's not a tensor. Okay. The Lagrangian is decomposed. I already emphasized when you do the Lagrangian, you are dealing with not with fields, but with potential. So you have additional problems. However, if you take care of these problems, let me say, if you do a bit of engineering, you get the Lagrangians, and these are independent. Okay. The symmetries I already said, I don't have time. Okay, what now? So far we have electromagnetism, so it's pure gauge. What about matter? In order to deal with matter, we need to deal with the Dirac equation. This is very difficult. Why? Well, because vectors and tensors are easy within quotes. Spinors are not easy. Spinors live in a complex space, or if I want to be mathematical, in a complex representation of some group. Okay, so the question is, how do spinors descend? Can we apply Hadamard? Yes, we can apply Hadamard. Otherwise I would not be here to give this seminar. Briefly, this is the Dirac equation. This is the Lagrangian, the Dirac equation, the gammas, and the Noether's currents. This is all we need to quantize or to deal with the Dirac equation. Let me say, when we go to slide 1, we were dealing with classical electromagnetism and external currents. Remember, these currents were given by God, God-given. You don't question. They are there because God put them there, charge and currents. When you have Dirac's, classical Dirac, you have equations, and then you have the currents. The currents are, in a sense, given within the theory. Okay. The Dirac equation, usually, I will work in the Dirac representation. So the Dirac equation is a phi component. We usually call this electron. And a lower component, chi, which we call positron. So the Dirac spinor is 4 fields, phi up, phi down, chi up, chi down. And the Dirac equation, again, is a differential equation of first order in time x, y, and z. So in the 4 coordinates of the Lorentz group. Okay, now what about the descent? In principle, we can apply the descent. You simply demand that psi does not depend on z. This is the requirement on the top right of the slide. When you require that psi does not depend on z, again, Dirac equation decouples into 2 sectors. It decouples in this curious way. Curious. There is the phi up component that is associated to the chi up component, while the down components are associated among themselves. I wrote the equation explicitly downstairs. The first set of equations depend on phi up and chi up. The second set of equations depend on phi down and chi down. These equations are independent. So if I can get, we are open to interpretation. Let me venture to give you an interpretation. When you give interpretation, you can be criticized. So I'm always careful. My interpretation is that when you apply Hadamard's descent, so when you assume the Dirac field does not depend on the third coordinate, you end up with a structureless particle with an antiparticle. In other words, there is phi up, chi up. Both particles have the same spin. So please do not think about the spin anymore. This is the same in the sector. The only things that matters is the fact that there is a particle and an antiparticle. They are reminiscent. They come from a spin 1/2 theory. But I would call this a structureless electron and a structureless positron. These equations stand on itself, you can have a look at it. It has an interesting structure, by the way. Okay. The two sectors can be transformed into each other by a symmetry transformation. So they are not really, they are independent, but they are related to each other. And interestingly, the two equations, the two Diracs that we get in 2+1 are graphene. So Hadamard's descent yields graphene. You may not be surprised. I was a little bit surprised when I got graphene out of a procedure. It's a procedure, it's Hadamard's procedure, and we get graphene out of it. Okay. Some remarks, because most of us are theoretical physicists, so you may be interested. We work in a particular representation, to Dirac, the standard representation. However, the descent can be made representation independent. A good theoretician must ask this question, and the answer is, can we make, does this depend on the representation? It should not, and fortunately, it does not. I will not linger on this, but you can work in a representation independent way by defining the right projectors. Let me tell you that if you work in a representation independent way, don't look at what I wrote here, just look at the final equation. You have two blocks, two sectors that split into psi plus and psi minus. And these two things are independent. Okay. So far, I did not give you many details on Dirac. However, we apply Hadamard's descent to pure gauge, electromagnetism, pure matter, Dirac, and things worked nicely. Although, let me emphasize again that when you descend with a tensor, you assume that the tensor that the fields do not depend on Z. You know what you're doing. You can make pictures. And Rocco made some beautiful pictures. When you do matter, you cannot draw things anymore because this is Dirac. It's a field, it's a complex field. So it becomes a little bit more complicated. So it is interesting in itself that the procedure works. Hadamard would not think of it. So the fact that it works, it's a kind of magic because it works in for a complex field. And we are descending in one real dimension. This is real space-time. Okay, what about interacting matter radiation? This is what we want. Okay, one way to couple the electromagnetic field with the Dirac field is through the minimal coupling prescription. The minimal coupling gives you F mu nu, Dirac Lagrangian, and look at the Lagrangian in the minimal coupling. I take that current. That coupling is A mu, J mu. J mu is the current. And J mu is psi bar gamma mu psi. Here, in the interacting field, the charge are not the sources derived from the fields. So you are not free to touch anything anymore. The theory is given. This is a complete theory. Now, we are we are used to this picture. However, now we have to apply Hadamard. And this is complicated. Hadamard, we have to apply with the minimal coupling, and we have to take into account the gauge prescription. Is that okay? Now, notice that there is already a problem here. When we apply Hadamard, we are forced to work with potentials. We cannot work with fields. E and B are not part of the picture anymore. You have to work with potentials. Okay, the two equations that you derive are Dirac-Maxwell. You are familiar with them. The first one is Dirac equation with a source. The last equation is the Maxwell equation written in terms of the potential with a source. I'm not applying any gauge. I'm not even taking the Lorentz gauge. These are the equations as they stand. Can we apply the theory? Can we apply the descent? Again, yes, we can apply the descent. I have no time to go into this also because I want to keep this seminar to a rather elementary level. What happens is the following. Of course, we are very lucky because I am very lucky because my collaborators are very good at drawing what's happening in this way. So you have on the right, we have Dirac's theory. You can independently apply the descent, go from 3 + 1 to 2 + 1, and you get two independent sectors that I call D plus and D minus. Independently look at the right hand side of the picture. We have electromagnetism. We go to 2 + 1. We have two sectors. One I called EEB, the other I called BBE. These two sectors are independent. Only one of them is tensor, EEB. Now, you couple, this is the part in purple. You couple Dirac and electromagnetism, and let me remind you, couple them through the minimal coupling prescription. What you end up with is Dirac plus electromagnetism in 2 + 1. Okay, it's not written anywhere that these procedures are consistent. Dirac is matter, electromagnetism is gauge, and when you couple them, you use a prescription. It's not written anywhere that this should work. It works, but partially. In other words, both theories, EEB plus D plus and EEB plus D minus, behave nicely with the tensorial electromagnetism. With EEB, you get two copies of graphene in a way. There is no way to consistently couple, no way. We could not find a way to consistently couple matter with the BBE field. Let me remind you briefly, that, sorry if I don't, I just go to this not in presentation mode. The EEB field is currents interacting with charge or cylinders interacting with lines. This is the theory that works, the so-called EEB sector. The other sector, BBE, we cannot consistently couple it to the matter field. We did not succeed. Okay, so let me go back. This is the diagram that summarizes everything. So when you apply the descent to Dirac plus electromagnetism from 3 + 1 to D plus 1, you get graphene, two copies of graphene. The other theory stands alone and it cannot be consistently coupled to matter. Of course, this is a prescription. I use the prescription, but in my opinion, it is useful. So when you go to quantum simulations, which is our main interest of lattice gauge theories, we know what we should look like. We should look at. We should look at presumably a version of electromagnetism in 2 + 1, but that looks like graphene. It is possible to conceive other theories, but these other theories do not admit a consistent coupling with matter. And this should worry us a little bit. Okay, so far so good for electromagnetism and Dirac. Now there are a lot of questions that you may ask about more complicated theory, statistical mechanics, about quantities that are of interest for the quantum simulations of lattice gauge theories, or the phase diagram of QED, the phase diagram of QCD. There are a lot of interesting questions. In my opinion, if you ask my opinion, we should look for quantum advantage. This will not be easy. Also because people doing elementary particle physics, they want result, they want quantities that they can compare with the experiment. And we all know that I think this is going to be difficult for the next 1, 2, 3, 4 years. So we should try and understand, in my opinion, what is meaningful, what we should do. Okay, this is a first step in this direction. I decided to put a last slide. This is the only references I gave. The first one is the paper that we published. Most of the work was done by Maggi, including the drawings. And so he deserves to be the first author. He just appeared. The other paper will be soon on the archive. And it's a paper that involves a number of people. I only quote the postdocs. and the doctoral students. So Angelone, Lonigro, Maggi, then there is other people, but most of the work is being done by the students. And it's a pleasure for me to acknowledge their contribution, which is crucial in this research. This work that will soon be on the archive, in my opinion, is a very interesting piece of work. We are continuing to work in this direction. I would like to conclude with an interesting quote that I often read by Chen-Ning Yang about gauge invariance. It appeared in Physics Today 2014. You know that Yang was a very profound thinker. He had gauge. Gauge for him was one of the mysteries of nature. And Yang used to say that I met Yang in Japan. So I remember when Yang was thinking, he was talking to Sudarshan and to sorry, I missed the name, the Dutch physicist doing statistical mechanics, who wrote a beautiful book. And there was a conversation among them. I was a student, or almost a student. And he used to say that Maxwell was a religious person. I wonder whether after this moment of discovery, he's talking about gauge invariance, he had in his prayers asked for God's forgiveness for revealing one of his greatest secrets. And I think gauge invariance is a deep secret of nature. So we should listen to what Yang says. Okay, I managed to finish within 50 minutes, and I would like to thank all of you for your kind attention. Thank you very much.
Thank you very much, Saverio, for this very nice and interesting and original topic, I would say. So the floor is open for questions.
May I ask you a question, Saverio? You have assumed that you have quantities which are Z independent, right? And
yes.
Therefore you assume that you have, in a way, a plane or something like that, something which is invariant under Z, okay? Now the question is, people doing graphene in particular nowadays worry about things like torsion. There is no geometry basically in your approach, but in fact, in people doing graphene, they are quite worried about geometry. I just wonder, because I was looking at your Dirac equation. In principle, you can do everything of Dirac equation in any coordinates. You can move the Dirac equation in any coordinates. And I wonder what would happen for your Hadamard procedure if you do that, okay, in principle. In particular, if you do that in spherical coordinates or something like that. And what is would be the role of torsion in this case for these kind of theories?
Yeah, it's a very good question. Thank you. I think Joao, I don't see who's asking question, but I think it's Joao.
Yes.
So, yeah. So what you get out of this procedure is exactly graphene. So in a sense, let me be my own detractor, there is nothing new. This is a procedure that gives you graphene. So if you ask me what is new, well, in a way, nothing. We start from 3 + 1 and we get to 2 + 1, which is graphene. So it is possible to conceive torsion. The advantage of the method is that you may think of torsion as something embedded in 3D, but torsion in itself should happen in a plane.
Yes. And
that's exactly what happens. Incidentally, these deep questions, you can go to this seminal contribution by Haldane, Thouless, and you know, the Nobel Prize of when was that? A few years ago. So you can conceive models in which there is torsion in 1 and 2 dimensional model. In 1 and 2 dimensional models, this gives you topological effects, and torsion can be considered. So in a way, since what we derive is graphene, the only advantage is that you have a new perspective. Feynman would say it's always interesting to look at the problem from different perspectives. Not because you get something new, the problem is the same. You're simply looking at it from a different perspective. So it will be, as a matter of fact, very interesting to look at this characteristics of graphene, what people are worrying about graphene by starting from 3 + 1. This can be done for sure, because we are getting graphene. So in a way, there is nothing new. So whatever can be done with graphene can be done with Hadamard's descent. Mm-hmm. So in a way, I'm not answering your question. What I'm saying is that in principle, everything can be done. And it will be very interesting to look at this. As a matter of fact, this is what was worth the Nobel Prize by Haldane and by, to derive topological effects from 1- and 2-dimensional models out of something else. So these are deep and interesting questions, Joao, which I'm thinking all the time about.
Okay, thank you.
Sorry, a comment about this previous question. Hello?
Please, yeah, I don't see who's asking the question. Let me stop sharing. So,
yeah, okay. Sorry, I don't have a camera. I have to.
This is Huri Ziaepur. Please go ahead.
Yeah, let's.
Very nice to meet you, Huri. Yes.
Yeah. Isn't it possible to, because everything that you are doing is local, therefore, even for graphene, if there is the torsion, I mean, the surface that you are considering, the space is curved with a redefinition of your frame, you can be able to at least locally explain everything, because everything you described also applies if the space is not, if you are not working in a Minkowski space, but in a curved space-time. Am I right or not?
I think this is this question is a bit more difficult. So let me go back to the previous question about torsion. You have a plane in which there is graphene. In this plane, you can describe anything within the plane without thinking of the third dimension. Now, if you think of twisting a layer of graphene and going to a magic angle, for example, twisting a layer of graphene, of course, you are breaking the Z symmetry that I was integrating out. Right? So you cannot hope to recover by Hadamard's descent effects in which you are physically twisting 2 layers of graphene. These effects are breaking the Z, the independence of the equation along Z. A similar problem, happened at the beginning of last century when they were trying to understand the Kaluza-Klein theories in 4+1 dimensions. They were trying to understand how to interpret this rotation in 4+1. This rotation should have given electromagnetism. They did not succeed because they were missing a phase. But these questions may require a completely different approach. So that's why it's interesting. So can we derive something looking like effects of graphene when you twist a little bit to independent planes of graphene? The answer is no. We hope to get a novel perspective, but the answer is clearly no, because you are breaking the invariance along the Z coordinates. Now, when you deal with Kaluza-Klein, there was an independent ingredient, which was the phase, and it was not understood at that time that the phase would become a gauge. It's very difficult. I am unable to answer this question. Can we play with the gauge and get something like Kaluza-Klein? I'm sorry, it's a very interesting question, but I cannot answer it. I'm unable to answer it.
Okay, thank you.
It's interesting.
Thank you. Are there any other questions? Someone maybe can look in YouTube and write it in the chat if there are any other questions for me. I don't know if Saga is doing that.
I don't see the chat. Oh yeah, I see the chat.
No, but...
Oh, sorry.
I checked and I think there's nothing.
Okay, good. So, Saverio, maybe I have one final question. So, regarding the nice graph that you were showing, essentially what you're telling us is that in principle we could choose one of the different QAD in 1D, and from the very first part of your talk, but then when going on and making the full theory with matter and so on, consistency will suggest that what we are doing is the right choice, essentially.
Yes.
That's very nice.
Yes, Simone, it's, of course, let me say, this is the comment of a mature physicist. So you are, I fully agree. It's a comment of mature physicists. You say consistency is suggesting that there are many choices, but somehow nature is picking one.
Yeah.
Yes, yes.
Because in principle, I don't see any other, we have to make some hypothesis or invoke some principle that I don't know to make the correct choice.
For example, you might demand that the theory is a tensor. Yeah, I don't know what this might be justified on the basis of mathematical elegance, but yes, indeed, yeah, you're right.
Okay, thank you very much. So with that, I will ask all the audience to thank you again, and with a virtual applause.
Thank you.
That we close the session, but before I would ask Raffaella if you can show the slides for the next seminar. Okay, so we can announce the next QuantERA seminar on the 13th of April, which will be delivered by Sofia Vallecorsa from CERN Quantum Initiative on quantum generative models in high energy physics. And with that, I would like to thank, next slide, I would like to thank all our organizers of these QuantEP seminars, Yasser Omar, Andres Ambainis, and Joao Seixas, and of course, the most important support of Raffaella and Ribeiro and Sagrar Pratasi. Thank you very much. Have a nice evening, and see you next month.
Thank you. Bye.
See you.